Hey, what's up, everyone? Mr. McKinney here. Today, we're going to look at how radical functions are used to model speeding tsunamis. If you checked out the assignment in Schoology, the intro assignment, and watched the video, hopefully you learned a little bit about tsunamis. These are giant waves created by underwater events such as underwater earthquakes, volcanic eruptions, or rock slides, commonly referred to as tidal waves, although they don't have anything to do with tides. And what we are going to do is we're going to take the role of scientists and look at how they use mathematical models to predict the speed and time it takes for a wave to travel a certain distance so they can warn people. Couple of catastrophic tsunamis in recent history. 2004, I believe, in the Indian Ocean, Indonesia, there was a terrible tsunami. And then more recently, 2011, maybe you heard about tsunami in Fukushima, Japan. It actually flooded a nuclear reactor, created a terrible environmental disaster. The whole nuclear plant melted down. It was like a worldwide environmental disaster caused by a tsunami. Just like at the end of the video in Schoology noted, the most effective way people have come up with to protect people from tsunamis is just to simply warn them as fast as they can. There's no way to stop them. This is literally a force of nature. And yeah, this is how they predict them, where they're going to be and when they'll get there. Um, So I'm going to walk you through some parts of the activity. I'm going to do one example, and then the rest will be up to you. First page, after the brief introduction, we get this big gray box. It has a lot of technical information that we're going to need to complete this activity. First off, we have our radical equation. It's called the wave speed formula here. And this equation is what we're going to use to model the speed of a tsunami. We'll see it written in one other way. It can be written as d of s equals the square root of 9.81 times d. So the speed in meters per second of a tsunami is equal to the square root of 9.81 times d. Now these two values here, 9.81, it comes from the acceleration caused due to gravity. If you watch the video, it had a really great visual of an underwater event, whether it's an earthquake or a volcanic eruption, releases this great amount of energy which pushes a huge mass of water vertically up into the air. It literally pushes the water up, and then it gets pulled back to the earth by the force of gravity. And this is where the wave is actually created. As the water crashes back into the ocean, the energy dissipates and ripples outwards, and that's how the wave is created. So this 9.81 comes from the force of gravity. This d value here is related to the depth of the water at the epicenter or the origin point of the tsunami. Because the deeper the water is, the more volume of water that can get pushed up, more volume of water that comes down, more energy, creates a bigger tsunami, more speed, etc. So the greater the depth, the more water that is moved, more energy, and so on. So multiplying these two and taking the square root will give us the speed of our tsunami. Now that's just one part of our activity that we're going to look at this week. A couple other things going on in here. This speed is going to be given in meters per second, but that's not the most useful way to communicate speed. If I told you that I could run 50 meters per second, I don't know what that would mean to you. I mean, maybe it sounds really fast, but typically we talk, miles per hour might be a more useful way to talk about how fast something is moving. So later on, we will be converting this not to miles per hour, but to kilometers per hour. a slightly more usable unit of measurement. So there's a couple conversions in here. And then we're going to calculate the distance the wave travels as well. We're going to be using the Pythagorean theorem, which we just covered a little bit ago, to triangulate, use some trigonometry to calculate the distance between 2 points. The epicenter of your tsunami and the city we're going to try and protect. They're not in a straight line, so we're actually going to create right triangles to calculate that distance. And then the last thing we're going to have to do is we are going to take our distance and speed and calculate the time it takes the wave to travel that distance. So 3 different calculations we're going to make. I believe there's about 3 different unit conversions we're going to make as well. And yeah, let's see if we can save some people. Last thing before we get started with the actual activity, we see here a graph of square root function. Hopefully this shape looks a little familiar. We worked with these a section or 2 ago. We see our speed function, and one way that this function is useful is if we looked at it on a graph, you could simply talk in general terms, like if there was a tsunami occurred at 8,000 meters, how fast would it be moving? Well, we can just move up our graph and make an estimate and say, well, that tsunami would be moving about 280 meters per second. Or if we had a tsunami that occurred in shallower water, 3,000 meters, how fast would that tsunami be moving? We could come up here and estimate. This one's not exactly on a cross point. It's a little over half. I'd say, maybe we could say 172 meters per second, right about there. So we can see that as the water gets deeper, the speed of the tsunami increases along the graph of the function. All right, so to get to it, your job as a scientist, you are going to have to select one of 2 scenarios. There's 2 catastrophic events you could choose from. The scenarios are located on the very back of your handout. We're going to pick a scenario. We're going to label the cities and the epicenter involved, and then we're going to use that information on the map to figure out the distance. We're going to calculate the speed and so on. Just pointing out, there is a step 3 that we're going to skip. It was asking to draw some concentric circles around the epicenter, creating a little bit of a visual of the danger zones. We're going to skip that part for our activity. So don't worry about number 3. Let's go to the back of the handout and pick a scenario. So I'm going to do part of scenario 3, which is not included in your handout. You will have scenarios 1 and 2 to choose from. You can do either one. I'm going to use part of 3 as my example. So scenario 3, accounts of violent shaking lasting around 30 seconds have been reported across the coast of Oregon. Initial details show the earthquake originated just off Astoria, Oregon, in the Cascadia subduction zone. Cities under imminent threat include Ocean Shores, Washington, Seaside, Oregon, and Crescent City, California. And then this event occurred at a depth of 5,000 meters off the coast in the ocean. So we're getting some important information from our scenario. I just underlined a few key things. This is our epicenter. So this point will be identified on our map. We have to identify our 3 cities that are in danger, and then my depth is included here. You'll find the same information in scenarios 1 or 2. Choose whichever one sounds more interesting to you. So I got my information. Let's go to our map. So here's the West Coast USA map. Our first step, we're going to label the important locations for our scenario. For my scenario number 3, the epicenter of my event is the Cascadia subduction zone. I'm going to abbreviate that as CSZ, and it is this point here. Now you can see all of these points are unlabeled, and some of them are actually really close together. There's 3 points in Alaska and 2 in Hawaii. You'll probably have to look up on a physical map or Google Maps some of these locations. So you'll have 4 per scenario. Google Map, check them out and label them here because I didn't have this memorized either. Cascadia subduction zone, this is an underwater fault. It is a point, it's a real place. It's a point where 2 tectonic plates are rubbing against each other. Cascadia is like the region. The word subduction, it means a point where one of the plates is pushing underneath the other plate. So they're rubbing against each other, and one's going under the other one, and one's going up. And that's the place where earthquakes occur when they move and shift. So this is a real underwater fault that actually creates, this is a real scenario of danger for this western part of the United States. I read some interesting stuff as I was looking up these locations, and I looked up the Cascadia subduction zone, and it has the potential to create a catastrophic tsunami that would really devastate the western part of our country. So, real place, and I'm going to label that one red. This is the epicenter of our event, our underwater earthquake. I was given the name of 3 cities that I'm going to try and protect by giving them a time. The earthquake happened. How long do they have to react? Seaside, Oregon is right here. I'm going to label that one in blue. Ocean Shores, Washington is right here. And then lastly, I'm going to abbreviate Crescent City, California is right there as well. So my scenario, I'm tasked with giving these 3 cities advance warning of this impending tsunami that is going to be coming at them. Okay, so we got our places labeled on the map. Let's go back to our instructions. Okay, boom, check. So I read my scenario. I picked number 3. I labeled the West Coast USA map. I marked my epicenter in red. Marked my land locations in blue. Check. We're skipping 3. We're not worried about drawing those concentric circles. On to step 4. Our first goal, we need to figure out how fast is this wave moving. That's going to be our first key to determining how long these people have to react to the tsunami. So we're going to use our wave speed formula. You can grab that from the gray box. Our wave speed formula is the square root 9.81 times our depth. Now the depth I got from my scenario description. My depth for my scenario is 5,000 meters. So we plug in our depth and our speed is approximately 221.47 meters per second. So there's our first calculation. Wave speed formula, plug in our depth, and we get our speed out, 221.47 meters per second. Next step, we're going to have to figure out the distance between the epicenter of our event and each of our cities we're trying to protect. So we have to go to our map, and we're going to have to deal with longitude and latitude a little bit here. So there's some information given to us here that longitude and latitude are measured in degrees, and we have to make a correlation between the number of degrees and a physical distance. In this case, we're going to use kilometers. So this information tells us that 1 degree of latitude is approximately 110 kilometers, and 1 degree of longitude is approximately 70 kilometers. So they're not the same. Let's check out our map. Some more information. Um, this is where we are going to do, if you've ever heard triangulation, we're going to use trigonometry. We're going to use the Pythagorean theorem. We're going to create a right triangle to calculate the distance between these 2 points. And just an example here you can check out later. Let's get to our map. All right. So I made a couple notes on my map. Latitude goes from east to west, left to right. So latitude is here, left to right, and 1 degree is 110 kilometers. Longitude goes north to south, 1 degree, 70 kilometers. Looking at our map, we have some lines indicating the latitude and longitude. Here, these lines are latitude, and they are separated at gaps of 15 degrees. And we can notice that they're not all the same width. The physical space between them is not the same. I can scroll up. The next gap is even bigger. This has to do with the fact that the Earth is round and we're looking at a flat map, but we're not going to get too caught up in that detail. That this physical gap seems bigger than this one, but they're both containing only 15 degrees of latitude. And the same thing is true if we look at the top for longitude. Each line is a gap of 15 degrees of longitude as well. So we're going to estimate as best we can the degrees of latitude and longitude between 2 points to create a right triangle and calculate the distance. So the first city I chose to calculate the distance for was Crescent City, California. So I need to figure out the distance between my epicenter and Crescent City. And what we're going to do is we're going to create a triangle. We're going to make a right triangle. I'm going to go directly across, lined up with Crescent City. We're going to make a right triangle like this and use the Pythagorean theorem to calculate the distance, which is going to be the hypotenuse. Now, the reason we can do this is because we can use the map to estimate the distance left to right and up and down using the lines of latitude and longitude. I'm going to do some estimation here. I have a blown up map I'll show you a little bit better, but I have to stay on this map for a second to show you kind of the lines I'm referencing because I'm using some techniques of estimation here. So my markers are on the top. They'll be on the top of your printout. But if I look at the longitude, this is 135. This one is 120. So I have my gap of 15 degrees here. Now my first estimation, I'm going to try and figure out this side of my right triangle, that top side. Now this red dot where my epicenter is, I think it's a fair estimation to say that's about halfway in between those. So I'm cutting down that gap about halfway. So I go from 15, now I have this gap of 7.5 degrees. Okay, so from the epicenter to this line is about 7.5 degrees. Now I need to get it down to wherever Crescent City is. So if I go down from Crescent City, Crescent City looks like it's a little less than half. So I'm estimating the distance from the epicenter to Crescent City along the top is a little less than half than 7.5. So I'm going to estimate it's about 3.5. Let me make sure I got that one the same. Yep. Okay. So I estimate the top part of my right triangle is about 3.5. Okay. Now I have to estimate the right side of my triangle here. Okay, so now I'm going to use the same idea with the latitude. So, I'm on this line of latitude here is 45, and I'm going to use this line of 30 down here. So I'm going to say my epicenter, it's close enough. I'm going to say it's right on that top line of 45. So I just have to figure out how far is Crescent City, and it's really close. It's not going to be very far off. So I'm going to have to cut it in half a few times. The idea is that I can estimate where half is, and as I get closer, it'll help me figure out where Crescent City is at. So if I cut my line of latitude in half again, so now I have a gap of 7.5 degrees. So I'm using that idea of cutting it in half on the map again. So then if I cut this in half again, or excuse me, if I cut 7.5 in half, now I know that that gap there is 3.75. And I'm still not quite up to Crescent City. I'm getting closer. I'm going from the 45 down, 3.75. In Crescent City, it looks like it's a little bit more than half. Okay, so we are doing estimation. I'm using this method of taking halves. And I've got it down to this section. My epicenter is on this 45, the 45 latitude here. And I got kind of 3.75 degrees marked out here. And I think Crescent City is a little less than half. So I took half of 3.75, which is 1.875, and I went a little bit less. So I said that this gap was about 1.85. So after all my work, this is what I did. I zoomed in, so now you can see my triangle. So this is Crescent City, and here's my epicenter. I went over and down, okay? Now I'm not doing anything with that dot. That's a different city. I just went over halfway, Crescent City, from my epicenter. We made a right triangle right here, okay? And by my estimations, I estimated that this side was about 3.5 degrees, and this side was about 1.85 degrees, okay? So we're creating a right triangle, and now I need to change these degrees into kilometers, and then we can calculate uh, the hypotenuse of our right triangle we created. Okay. So your points will be a bit spread out. You'll have more space to do a triangle. Mine were close together, but you're going to do the same technique. You're going to create a right triangle using just 2 points. I know this corner seems like it's on that blue dot, but it's not. This corner is just directly over this blue dot here. So we made a right triangle connecting these two dots, estimated these two sides using the map. Now we're going to use the Pythagorean theorem to calculate the hypotenuse of our right triangle. See if I can get back to my space here. So that was our time. Okay, so here we go. This is the place where I'm going to put in my distance. I'm doing scenario 3, and I'm calculating the distance from the epicenter to Crescent City. So I'll redraw my triangle just to show you my calculations. This is our CSZ. This is Crescent City down here. Now I have to change my degrees to kilometers. Now I had 3.5 degrees. This is my longitude. 3.5 degrees. We get 70 kilometers for every for every 1 degree. So that's about 245 kilometers. So this distance was my longitude, 3.5 degrees times 70. I get 245 kilometers. Now my latitude here was 1.85 degrees. And for latitude, we get 110 kilometers for every 1 degree. So I got 206.25 kilometers. And I just got a small error made in my calculations. I actually had this is 1.875. So even if I went back to my map, apparently I adjusted my estimation and I decided this was 1.875. Oh, terrible. But so just making sure my numbers are correct if you check them yourself. 1.875 degrees times 110 kilometers. I get 206.25. So now we have our right triangle in kilometers that we created. I redrew it here, just showing the subduction zone to Crescent City. Estimated this distance in degrees, changed it to kilometers, change this to kilometers. Now we can use our Pythagorean theorem because I have the two legs and we want to know what is our hypotenuse. So now we can set up the Pythagorean theorem. Say, well, 245 squared plus 206.25 squared equals c squared. Using the calculator, I just plugged these two into the calculator. I said 245 squared plus 206.25 squared. I got 102,564.0625 equals c squared. And I didn't round it off. We will round it later, but you always want to wait till the very end. If you round it in the middle, it actually could affect your final calculation more significantly than you might imagine. So we will round this, but not in the middle. I'm going to wait till the end to round it off. So here we got 102,564.0625 equals c squared. And using the stuff we've been studying in class recently, I can solve for c by taking the square root of both sides. Tells me that my hypotenuse, which is the distance, is about 320.256, and now we are in kilometers. So we found our distance, and to make it usable, we are going to round it to the nearest whole kilometer. So we will just say that is 320 kilometers. Okay. So Pythagorean theorem, we found our distance. Now I'm going to go ahead and show you how to finish it. I'm only going to do this 1 out of 3. So again, you're going to pick one scenario. So you'll have to find 3 distances. And then the last part, we found our distance. Now we have to find the time. Because imagine we're doing our work as scientists. Earthquake happens here. We found this distance. We said, okay, they're about 320 kilometers away. how much time do they have to prepare for the tsunami? So the last thing we have to calculate is time. Okay, and our time formula looks like this. Again, you can find this in that gray box on the front page, but time is equal to the distance divided by the speed. So we have some information I'm going to bring back to our page here. Our distance is about 320 kilometers. Now our speed, let me grab our speed. 221.47 meters per second. So at this step, we're going to need to change our speed to kilometers per hour. The kilometers have to match up because when we do this calculation, we don't want to have kilometers over meters because some bad math will happen there. We want kilometers over kilometers, and we're going to change it from seconds to hours because it will be more usable. It would be more useful to talk in hours and minutes rather than like, oh, you have 5,000 seconds to prepare for this tsunami. You'd be like, well, you have an hour and 20 minutes, or you have 15 minutes. It's just more natural to speak in those terms. So this is where we're going to do our last conversion, and we have to convert our speed from meters per second. We're going to go to kilometers per hour. So that conversion is going to look like this: 221.47 meters per second. So this is something that you would see in chemistry or in certain sciences a lot, where we have our meters over our seconds. We can set up other ratios to cancel them out and change the units. So the first thing I'm going to change is meters to kilometers. So there's 1 kilometer for every 1,000 meters. And when I talk about canceling, we can set up these ratios where meters divided by meters is going to cancel out. So our ratio has to match. There's 1 kilometer for every 1,000 meters. And when we do this multiplication, we'll multiply this by 1. So on top, we have 221.47 meters divided by meters cancels out. So we're left with kilometers on top. And then on bottom, we have 1 second times 1,000. Well, we have 1,000 seconds. So then I could divide those two. And we could say 221.47 divided by 1,000. We're going to get 0.22147 kilometers for every 1 second. Okay. So we changed it to kilometers, but this is a really weird number. You'd be like, well, 0.2 kilometers doesn't mean much for every second. We want to change that to hours. So we can use this same conversion idea. We can say, well, if we have 0.22147 kilometers for every 1 second of time, I want to change it to hours. So I want the seconds on top so that it will cancel out. And there's 60 seconds in a minute and 60 minutes in an hour. So if we multiply those together, there's 3,600 seconds for every 1 hour. So we can create this ratio of seconds to hours. If we multiply these together, the seconds will cancel out and we'll be left with hours. So seconds divided by seconds cancels. 1 times 1 on the bottom. Now we're in hours. Up top, 0.22147 times 3,600. 797.292 kilometers per hour. Okay, and we could just write that as 797.292 kilometers per hour. Right? So that's our last conversion. So we changed our speed, 797.292 kilometers per hour. I have my speed and distance, and I can use the time formula to finish. So our time is equal to our distance, 320 kilometers, divided by 797.292 kilometers per hour. And we can see when we divide again, the kilometers are going to cancel. We have kilometers over kilometers. So those two units will cancel out, and we'll be left with hours, which is just our time. Okay? So grabbing the calculator again, 320 kilometers divided by 797.292 gives us approximately, so I'm going to round at the very end because it's like 401,358,599. So we're going to say approximately 0.4 hours. Okay, so it's a little less than half an hour. We say, well, you got 0.4 hours. Maybe we'll change that to minutes. We can say 0.4 hours. We multiply that by 60. That's going to give us our minutes. 0.4 times 60. The city of Crescent City, California, has 24 minutes to prepare for the tsunami that originates in the Cascadia subduction zone. Time to run. So that's all our math there. Watch this video if you need some guidance. There is a fully worked out example in the handout. Show up for the Thursday morning Zoom if you have questions, if you try it and you get stuck. At the very end, this is kind of just putting it in perspective. This would just be your own ideas. Maybe you can do a little research. List below some ways people at the locations might prepare and or react to the approaching tsunami in each scenario. Again, you're choosing one scenario, but you will have 3 locations. Take into account differences there may be with the amount of time they will have before the tsunami arrives. For example, Crescent City, abbreviated CC, 24 minutes from the time the earthquake occurs till the time it hits the coast at that point. What do those people have time to do? How long would it take for them to get the warning? So this is like the application part here. An earthquake occurs at that point, Cascadia subduction zone. In 24 minutes, it's going to hit the shore in Crescent City. What do people who live there have time to do? And again, I'm not an expert on this part. I might do a little more research if I couldn't think of anything. What I would probably do is they probably jump in their car and drive as fast as they can inland. Like, you wouldn't have time to pack. You wouldn't have time to like lock your house up. Hopefully you're around your family. I don't know. 24 minutes, not that long. It would be like get up and run. So the cities that you are trying to save, your times will be different. Your people might have time to do different stuff to prepare. So this part, just come up with your ideas. What do you think? All right, thanks for watching. Hope to see you all in the Zoom and talk to you all soon.